If you don't know anything about effect handlers, I'm sure you will know something after this talk. If you already know something about effect handlers, I'm sure you're eager to know what's happening on the front line of research. All right, so this is Valentine's Day. I'm going to talk about what we love about functional programming. And in this talk, we'll have two parts. First, some theory, and then I will show you some code in our language that we develop at Wrocław, which is like the cutting edge, most advanced language with algebraic effects in the world. And just a disclaimer, I will be talking about like a direct style algebraic effect, so nothing monadic will happen here. All right, so Valentine's Day. So if you ask people why they love functional programming, you will often see this picture. People will say, okay, so functional programming is so cool because things are pure. Because our whole system, our whole program is composed out of very simple components, functions. They take some inputs, they produce some outputs, and then you build like from smaller functions, bigger functions, and the entire system is a bit like that. So it's very modular. Testing is as easy as it could be, and refactoring is easy. Everything's easy and beautiful, except for, it's not really true. I mean, very often we do want to benefit from some under-the-hood magic, and it is nothing bad, right? I mean, we often say that we really, really love purity, but there are a lot of situations when we really want to use some effects, like exceptions. So when you compose your program out of smaller parts, and each part can fail, and you want to propagate this failure like, outside of your whole component, then you can use exceptions. You can program against an assumption that everything goes smoothly, and only if one of the part fails, then the entire component fails, right? So it's nothing bad about exceptions. Some algorithms just are easier to express when you have access to mutable state. So computational effects, right? All these things are called computational effects. When you do some input-output, you do exceptions, mutable state, backtracking, logging, concurrency, you memorize something, you have some control operations, continuations, call CC, things like that. You generate some random value, you generate some fresh identifier. The list goes on. And moreover, it's not only that you use some of these effects, you also want to mix them together. Like you want to have a program that uses 5 different effects, and it's not only a matter of being able to use 5 different effects, it's also a matter of being able to specify what the interaction between the effect is. We'll get back to that, right? So I believe, and this is my assumption today, that purity is very fine and very good, but computational effects are also very good. But you have to use them in the right way, right? You need to know what you are doing, not to mess up your entire program, right? So the question and the things that we work on, so the question is, what can the language give you? Like what kind of support can your programming language give you so that you can program with effects in the right way, so that it's safe, expressive, and well, pleasant, right? There are, I think, 2 usual approaches to computational effects. One is what I call God-given effects. Like if you program in OCaml or Scheme or something like that, a call-by-value language, then you usually have access to some predefined set of effects. Like you can throw an exception, you can like create a mutable reference, you can do some continuations, you can do some I/O. Like, you can do these things in OCaml. So there are some pros and cons for this approach. So the one pro is that you just use them, right? You don't have to really worry about structuring your program in a different way or something like that. You just want to throw an exception, you don't have to think about it much. But there are some really bad things about this approach to effects. First of all, you only have a small predefined set of effects. Like, we had like a long list on the previous slide, but here you have like 5 different effects in let's say, OCaml. And then you have to code your way around this to achieve a different effect, like generating a fresh identifier. If you want to generate a fresh identifier, you probably need to build it over like this mutable state thing or something like that. So this way you lose some, you don't have some expressivity because you only have to work with a predefined set of effects. Second of all, effects are not tracked in types, right? You see a function unit to unit in OCaml, you have no idea what it does, right? Usually you say, okay, types are so cool because they tell you so much about your functions, but, well, unit to unit, it can do anything because it can have some side effects, right? So types don't give you any guarantees, actually. They give you some intuitions, maybe, but not guarantees. And then another issue is the fixed interaction between effects. So consider a scenario when you want to have both exceptions and mutable state, and you want something like transactional state. So when you throw an exception, your mutable state needs to go back to its original value, right? So it's not easy to, even though you have both exceptions and mutable state in OCaml, it is rather difficult to obtain this transactional state behavior. Well, maybe it's not difficult, but it's not an effect you have to code around. You have to be very creative. All right, so there are other approaches. So in Haskell, for example, we have monads. So I also have some data visualization. Do you enjoy programming with monads? So I say the red piece of pie is yes, I do. The green one is no, because I don't understand monads, and the blue one is no, because I understand them all too well. So do you enjoy programming with monads? Let's vote. I do. Doesn't mean I don't want something better, right? So I'd say it's not this scenario, but it's a joke. All right. So how about monads? Is it a good approach? So obviously, some pros and cons. The good thing about monads is that they allow you to define your own effects, right? Then you have this long list of effects that you would like to have, and you can just define them. You can have a monad for fresh identifier generation. You can have a monad for transactional state, things like that. Not a problem. And also, they are not, like, effects are not tracked in types. So now you know what your function unit to unit does. Well, maybe not all effects, like non-termination. Some people consider it an effect, but now effects are tracked in types so that you know if your function actually needs to use mutable state or that it can throw an exception. But there are some bad things about monads that I don't like this monadic style of programming. I don't like it. I mean, it's like imperative programming for me. You do this, do this, do this, do this, do this, right? I don't like monadic style of programming. It makes things difficult, like code refactoring. So no. And then there are some known modularity issues. You have to work with transformer stack, which is very inconvenient. Obviously, there are some solutions to all these problems, but still, I don't think this monadic style of programming is perfect. So, still looking for something better. The approach I want to talk to you about today is called effect handlers. And By that, I mean direct style effect handlers and algebraic effects. So there are some experimental languages now that implement that. They're called Frank, Coca, Lynx, Helium. And they're actually not that new. I mean, the whole idea for algebraic effects and effect handlers, they originated in the early 2000s in some papers by Gordon Plotkin and John Power. And so what are the good things? Can we now have the cake and eat the cake, right? Yes, now we can define our own effects. Yes, we can track them in types. Yes, we can have direct style of programming, so we can refactor our code. If we need to add somewhere deep in the code one single expression that throws an exception, yes, we can do that. And then we can define what we mean by interaction between effects. So we not only can define different effects, we can only specify how they interact. Obviously, this is still rather experimental. There are a lot of things we still don't know about effect handlers. Okay, there are some theoretical problems still, but we still don't know the pragmatics, right? Someone needs to sit down and write a lot of code and tell us how to use algebraic effects and effect handlers. Okay, so let's see that in action, right? It's easy to say that it's just the good things. So I want to show you, first I will tell you what effect handlers are, okay? So the idea behind effect handlers is to split the definition of an effect into two parts. One part is just a set of operations. You say that if I want to do exceptions, I have an operation throw, just as a, let's say, syntactic being. No semantics associated with throw. Just you say, I have throw. If you want to do mutable state, you just declare you have an operation put and an operation get. If you want to do some nondeterminism, you just say, I have an operation flip, which will non-deterministically give me true or false. Okay, and the second part is called a handler. So a handler interprets these operations. By that, I mean that if you have a computation or an expression with some operations in it, you put it in a handler, and then when you try to evaluate this expression and you try to evaluate an operation, then the handler, which is like around your expression, takes control over this, and it is the job of the handler to decide what to do next. It is kind of like with usual exceptions and exception handlers. You just compute, but you throw an exception, which means you go back to your handler and the handler decides what to do next. So this is kind of a generalization of the usual exception handlers. We will see that in a moment. Okay, so I want to show you the thing that we produce at Wrocław, a language codenamed Helium. It is, as I said, it's very experimental. We don't have enough manpower to produce something really usable, but I think we can produce something I can show you. And this is, the current implementation is very fresh because it's based on a paper we had this year. So we didn't have enough time to like, fix all the bugs. All right, so it is on Docker. You can just run it. I will show you some syntax in a moment. All right, so let me give you some examples. Okay, so more about the language. So, it, of course, it has effect handlers. It has the new feature called effect instances. When you want to have two cells of mutable state, right? It was a problem a year ago. You wanted not only state, but you wanted two cells of mutable state. How to do that? Well, it sounds silly, but we didn't know that a year ago. Now we know. It has quite an advanced type and effect system with a lot of polymorphism in strange places. We don't need row types if you're interested in effect handlers. That is the new thing. And we have effect abstraction. That means we can hide the definition of an effect. This was also a kind of a theoretical problem because abstract effects are much more difficult to implement than abstract data types, where you can just delete the types and everything will be fine. It's different with computational effects. And it's a very strong module system. But it is a research level software. So it's for language hackers, I say at the moment. So a very poor documentation. OK, so let's see an example of that, right? And the first example will be about exceptions. So let me just make it slightly bigger. Lambda Days, let's call it M. Oh, it's per buffer, right? All right, so let's define exceptions. Now we can do that. Like we say, let's call it error. Right? We declare a new effect called error, and we say there's one operation there. It's called throw, and its type is for all A. Type, its unit, to A. Okay? And that's it. That's the whole definition of an effect. Not whole, the first part, the signature of the signature of an effect, saying, I have one operation throw, and I will tell you in a moment what to do with it. OK, let me save this file and go to the interpreter. And I run the interpreter, and it says IORE. So the interpreter tells me that now I can use these two effects. Those are two built-in effects. One is input-output, and one is runtime error. So I can do like print int 6, and it will just print 6. Not very surprising. All right, so now I can import my file. And I can open the M module. And now I can ask the system for the type of throw. What's the type of throw? Dear system, and it gives me this long type, but it kind of says it's unit to A for any A, where different A is an error. So notice there are some apostrophes and back quotes. Those are two different A's. This is like the good human-computer interaction style, right? All right, so OK, now let's throw an exception. Well, +1, so that it's a real expression. What will happen? The answer is nothing will happen, because the system will tell me type error. I just told you I can use I/O and runtime error. I cannot throw exceptions, because the system keeps track of types and effects. It tells me here I cannot use exceptions, because the type says I can use I/O and runtime error. OK, so let's write a handler. Right, and how do I do that? I can say let some function foo equals to handle, then some computation, 1 plus throw, with throw 100. Well, this looks exactly like an exception handler. Like you throw, and if there is an exception, you just say delete that, say 100. OK. Now, oh, syntax error. Forgot the arguments to the operation. All right, so yeah, I need to import, I need to open, and now I can call this function foo with some argument unit and use just 100, because that is what my handler told me. So what just happened? So the system tried to evaluate this expression, this 1 plus throw, and then the system, it didn't know what to do with throw. So say, OK, handler on the outside, do something about it. And the handler says, OK, whenever you see the operation throw, just end the computation and give me 100. So I can, the nice thing about programming with handlers is that you can define different handlers for the same effect. So I can say, OK, that is this kind of default value handler, but I can define a handler that goes to the option data type, right? So I can say let h option is a handler. Handlers are, of course, first-class values. Why not? And I say whenever you throw something, then I say none. None is just like nothing in Haskell, and if you're a Haskell person. And then if there are no operations, just pure value, I can add a return clause and say whenever there is a value and not an operation, I say sum x, right? Let's save it. And now I think I can reload everything. Don't ask me why I have to do that. Right? And now I have this handler hopt. I can ask for its type, of course, which is saying that it handles error into option. Right? And then I can do handle 1 plus throw with hopt. Right? And it tells me none. Right? So the thing is that in here, not in here, inside this computation that I use throw, I don't have to say anything about option. Right? Only the handler knows about option, so the handler knows what to do with my operation throw, and then it can pack the result in the option data type or return nothing. OK, that's just kind of exception handlers. So let's do something more creative. And let's do reader. Reader is a type. And I say there's one operation ask, which is of type unit to s. And I will write a handler for that. Let h reader. Well, let's say v, like a value for the red stuff, is a handler. And I need to interpret the ask operation. Ask takes unit as its argument, so ignore that. And now, what can I do with this computation? What I want to do is not to just delete it, as in the case of exceptions. I want to continue. I want to resume the computation, but with the red value, the value that I just read or asked for, instead of this operation ask. Right? So I can use a keyword resume. This is the difference between exception handlers and general handlers. Resume v. This means that the semantics for this is that you try to compute, and then you try to compute the ask operation. The handler takes over the control, and it says and it tells us what to do with the ask operation. And this particular handler tells us resume the computation with v, let's say replaced, like the operation ask replaced with v. Right? So save this, close this, run this, import this, open this. And now I can write things like handle ask plus ask with h, what was the name of the handler? hreader 6, right? And now I get what I expected, 12. Right, so I just defined exceptions and then the reader effect. And as you can see, I just use this effect indirect style. I just put the operations in the code and not in any monadic do notation or anything. Okay, something more interesting. Signature nondeterminism. When I have a fail, which is of type unit, and I have flip, as in flip a coin, unit into bool. Okay, I can write a handler for that. Obviously, I have a choice what kind of handler I want. And I say I want the handler to just keep everything, like all the results, on a list, as in the case of the list monad. So I say let h nondet is a handler. Well, I do return x, right? When there is no operation, just a pure value, what do? I say, okay, there is one result, so I have a singleton list, right? Looks almost like Haskell. Now, whenever I fail, what do? I say, oh, the result is just empty list. And when I do flip, I say, oh, so there is a flip operation somewhere in the code. What does this mean? This means, at this point, the programmer wants to flip a coin and she wants to get true or false. And then I want to collect all the results on the list. So I can do resume true, which will just continue the computation with true instead of that flip. And then resume true is just the result of that. A result, so I can do something with this result. For example, I can append it to resume false. Like add symbol is append in the style of ML languages. And that's it. And then I can have let function, I don't know, q is equal to if flip, then 4 else 5, right? Now, let's try and test this program. Right, what do? I do this, I do this, I do this, and I say, what's the name of the function? Q unit, and oh, there's an error. Why? Well, obviously, because I forgot to put the handler around this computation, right? So it tells me type error. You try to use nondeterminism. Q uses nondeterminism because it flips a coin. But then I do not handle this nondeterminism, so it just told me type error. Okay, so let's handle this. Handle Q with H nondet. What? No pretty printing for lists, sorry. And it just told me for 5, 2 possible results of my computation. Okay, I have enough time for state. I do. Okay, signature, this will be the last effect, okay? You already know the pattern for defining signatures, I'm sure. So I want state to be parameterized by a type of state, of course. And then I need how many operations? 2. Put, which is of type, well, S to unit, and get, which is of type unit to S, right? Because I can put state, and I can get this current state. Let H state initial state is a handler. Okay, how to handle state? Well, we will need one more clause in the handler. So the type of the thing that will carry the computation, just as lists in case of nondeterminism, will be just functions from state to values, right? So in particular, when we see a pure value with no operations, we say, okay, the interpretation for this is a function from some initial state that always gives me x. Okay, now I need to interpret put of some state S, put some state S, which is, I take the initial state, but I don't care about it because I just came up with a new state. So what do I do? Well, there is a put operation in my computation, but what do I do next with the computation? Well, I just say, okay, the new state is put, continue with the computation. So I just do resume with unit, because put is an operation from S to unit, so I need to resume with unit. And then the resume unit will give me what? Will give me a function. So I need to give some state to this function. And it is obviously S, because it's my new state. And I can also get something. And I say, oh, get is easier, because there is some state S, which is my initial state. And what I do now, obviously I resume with what? So instead of the operation get, I want to, well, have the current state, because that's what get should do. So I resume with S, and then I resume S gives me back a function. So I need to apply it to the current state, which is, of course, S. And then there's one more clause called finally, which says, okay, when everything's done, just do the final cleanup. And the final cleanup is F is the final value of this handler, almost final, right? And then what do I do with F? So F is this function from state to value. So I say, okay, so give me the initial state. All right. And I can write now functions like let update F equals to put F get, something like this, right? Direct style. And I can do things like let inc n equals to n plus 1. All right. And now I can write a code, a piece of code like this, like import m. Oh, syntax error. Okay, so now I can handle some stateful computation, like, I don't know, put 5 update inc get with h state 7, right? Which means I have this computation which puts 5, updates the state with the increment function, and then gets the current state. So the answer is 6, right? Because I put 5 and then I increased this 5 by 1. All right. So the last thing is, how about using two effects together? Well, there are two ways to put together state, two obvious ways to put together state and non-determinism. One is when you have this state that is persistent, which is global, that it is shared between different non-deterministic branches. So when you backtrack, you still have the previous state, the previous, in the sense, left to you by the previous branch. And there is also the other direction, when each branch has its own cell. So if you put something, you do non-deterministic choice, and then you put something, then the original value is like the initial value for the second branch, right? So can we express these things? Well, let's try it. So let me say this. Let t, function t, is this. If flip, then update inc, and then get the current state, or else update inc and get the current state. So it seems like a very silly if statement or if expression, but it is not, because we have effects inside. And so we can say, okay, now of course I need to close this and open this again. I told you we don't have enough manpower to do all this boring stuff, like sensible file loading. I can do handle T of unit with H nondet with H state 10. All right? It's 1112. Handle T with H state 10 with H nondet. Right? It's 1111. Why? Because 1 is this version where the state is local. So when I flip both branches, the then branch, the else branch, has their own state. So initially it is 10. And so after increment it's 11. So it is 11 in both branches. But in the first version, when I first do the handler for state, this state is shared between non-deterministic calls, which means I first do the then branch, and I get 11, and then I backtrack to the else branch, but with the state given to me by the then branch. So I increment 11 to 12. So I got this global state version. And if you think about it, this global state version is not very easy to express in Haskell. So I did that recently. I programmed some backtracking search with some clever search space pruning, and I needed this, the backtracking thing with the global state, and I didn't even think to do it using a monad. I just did it using some continuations, not as a choice. Just it felt more natural to me, just because this effect is not very natural if you try to express it using monads. And here, no problem. You just put handlers in the right direction. So that's the end of the demo and the end of my talk, really. If you want to play around with our implementation, go ahead. There are some examples there, so you can, and some very short tutorial. But as you can see, it's still work in heavy progress. So, but if any of you wants to play with this, go ahead and do ask me questions. Thank you very much.
We have 5 or so minutes for questions.
Yes.
Yes, thank you. It was very nice. I wonder, you said you don't like this monadic style of writing programs and prefer this direct style, right? But I wonder, isn't it a bit dishonest if in direct style you have state and you have sum of two expressions, then in which order are these expressions evaluated? Why is it so natural?
So because this is a call by value language, then the order is just left to right, always in the case of like if you construct a tuple with put and put, the elements of the tuple are evaluated from left to right, right? Because you kind of use these effects as you'd use effects in OCaml, but in a more principled, user-defined and type-safe way.
So you have to know that you're in call by value. If you were in call by name, the result would be different.
That would be different, yes.
Okay.
Well, I'm sure it's like a personal preference. Of one over the other, yeah.
Thank you for the talk. So in Helium, is memory allocation considered an effect?
Say that again, please.
Is memory allocation considered an effect?
This is one of the open problems: how to do SML style or OCaml style mutable references. It is not clear yet how to do that. So at the moment, no. At the moment, you just have this. This mutable state in the sense of the state monad. You can always somehow simulate this by having like a huge state called the store and then add cells there. But you know that would also be a bit dishonest. But it's an important open problem, I'd say.
What is the type signature of the T function?
of the t function. Well, the function t, well, is this. It says I have an instance of nondeterminism. I have an instance of state. I get some a, and then I produce int. And the effect here is AB, where A is an instance of nondeterminism and B is an instance of state.
Hi, yeah. This looks really good, and it reminds me a lot of extensible effects, which seem to be quite similar in the way you handle, for example, a given effect and then return a value.
Yeah, sure.
This looks a lot more succinct and nicer in many ways, and I was wondering, is there anything that you can't express using this approach, effect handlers, that is easier or possible to express with monads?
So extensible effects is a library which is based on the same ideas. So they are very similar. So extensible effect is more or less like an implementation of the denotational semantics of this language. So it's as usual with Haskell, right? So we have a call by value language, and then if you want the same thing in Haskell, you actually implement its operation, its denotational semantics. So it's the same with monads, the same with algebraic effects here.
Hi, so I have two questions. First of all, is Helium dependently typed?
So the dependent type, can you please say that again?
Is Helium dependently typed?
Dependently typed?
Yes.
No, it is not dependently typed, although it has quite expressive type system to have this 1ML style module system. And there are some, it is one step closer to dependent types than Haskell.
Okay, so the other question that I have is that this thing about limited scope and all that, having watched talks on Coca, I thought that that's a solved problem. So my impression was that Coca has already solved that. Is that not true?
But what problem?
Like you showed us this paper that you were submitting, or you have just submitted, and it was like these things at night and the other ones at day, and it was about limited scope.
So it's about effect instances. When you don't just use state, you have a number of instances for the same effect, like two different mutable cells, which you use as two different effects, and then you need to be able to distinguish between the two instances, and so Coca and Frank, they don't have anything like this. There was something like that in F, but it was they removed that for a reason. Like their approach was different than ours.
Right. Okay. Thank you.
Okay. Thank you.
Let's give our speaker a closing round of applause.
All right. Thank you.